The paper titled System 2 Reasoning via Generality and Adaptation by Sejin Kim and Sundong Kim examines the limitations of current AI models in achieving deep logical reasoning, System 2 reasoning, which is essential for artificial general intelligence, AGI. Here is a detailed summary. Introduction. The authors highlight that while AI has advanced in task-specific applications using neural networks, reinforcement learning, and language models, these models struggle with abstract reasoning and adaptation, key features of System 2 reasoning. System 2 reasoning involves logical deduction, abstract thought, and the ability to adapt to novel situations, unlike System 1 reasoning, which is fast and based on pattern recognition. The paper identifies the need for AI models to generalize knowledge and adapt to unfamiliar tasks to progress toward AGI. Key concepts: System 1 and System 2 reasoning. System 1 reasoning is intuitive, fast, and pattern-based, typically used in familiar situations. In contrast, System 2 reasoning is deliberate, logical, and necessary for solving complex, unfamiliar tasks. AI models today primarily rely on System 1 reasoning, making them effective in narrow, task-specific contexts, but lacking the flexibility to handle new, abstract problems. To achieve AGI, AI models must incorporate both System 1 and System 2 reasoning. Generality and adaptation, critical components of AGI. The two critical components for System 2 reasoning are: 1. Generality, the ability to apply learned knowledge to new and different contexts. 2. Adaptation, the ability to modify behavior based on changes in the environment. Current AI models struggle with these aspects because they rely heavily on large amounts of training data. The paper emphasizes that AGI requires models that can generalize beyond training data and adapt to dynamic, real-world environments. ARC benchmark for measuring reasoning. The abstraction and reasoning corpus, ARC, is introduced as a benchmark to evaluate AI's ability to generalize and adapt. ARC tasks require AI to infer abstract rules from limited examples, testing generality and adaptation without relying on extensive training data. It is designed to assess System 2 reasoning capabilities in AI. Analysis of existing approaches. The paper reviews three current approaches in AI. 1. Program synthesis. This method generates programs to solve tasks based on given specifications. While it allows abstract reasoning, it is limited by the constraints of predefined domain-specific languages, DSLs, which restrict generality and adaptation. 2. Large language models, LLMs. LLMs excel in generalizing across tasks based on vast amounts of pre-training data, but they struggle with true adaptation. They tend to interpolate based on training data rather than reasoning abstractly in novel situations. Transformers. These models, used widely in tasks like natural language processing and image recognition, enhance generality through pattern recognition, but also face adaptation challenges when confronted with unfamiliar tasks that require logical reasoning beyond predefined structures. Proposed research directions for System 2 reasoning. To address the limitations of existing models, the authors propose 4 research directions. 1. Learning human intentions from action sequences. By capturing human intentions, AI can enhance logical deduction. Techniques such as topic modeling, sequential pattern mining, SPM, and hidden Markov models, HMMs, are recommended for inferring intentions from human behavior, which can improve AI's reasoning and adaptability. 2. Combining symbolic and neural models, a hybrid approach that integrates neural networks for pattern recognition and symbolic reasoning for logical deduction, is proposed. This would enhance both abstraction and generalization. Techniques like neurosymbolic programming, NSP, and differentiable inductive logic programming, TILP, are highlighted as ways to improve reasoning by blending symbolic logic with neural methods. 3. Meta-learning for adaptation. Meta-learning enables AI to learn how to learn, facilitating faster adaptation to new environments and tasks. By training AI models to generalize the learning process itself, meta-learning helps AI systems respond flexibly to novel challenges. 4. Reinforcement learning for multi-step reasoning. Reinforcement learning helps AI learn through trial and error. Advanced RL techniques such as hierarchical RL and model-based RL allow AI to adapt dynamically and perform multi-step reasoning, which is essential for handling complex tasks. Conclusion. The paper concludes that achieving System 2 reasoning in AI requires combining generality and adaptation in ways that go beyond existing models. The proposed research directions aim to bridge the gap between current AI systems and AGI level reasoning. By focusing on learning from human intentions, integrating symbolic and neural models, applying meta learning, and using reinforcement learning, AI can advance toward deeper, more flexible reasoning capabilities. This paper presents a roadmap for enhancing the reasoning abilities of AI models, bringing them closer to AGI by focusing on abstract thought, logical deduction, and adaptation to novel environments.